I should record to the computer. The second question is, are you going to define specification?
Of course, I'm going to define.
Okay.
But
Okay.
let me. So you see, I stated the problem, of course, and we have the following problems with that problem. It's first to answer what does it mean to classify, and actually later what is the answer for this class. So I would like to start with dealing with the first problem, which is what do we mean by classification? And only later I will pass to details about specification. So please, I may mention please I may mention some notions, but everything which is necessary to understand this talk will be defined. So no worries. So now now let me pass to this general setting. So what we are dealing with, we have a finite set A, which we call the alphabet. We consider all A valued B infinite sequences. So that's a set A to the Z. And once we take the discrete topology on A, then A to the Z becomes a compact metric space. Actually, as a compact metric space, that's a metrizable space. And as a metrizable space, that compact topological space is homeomorphic to the usual Cantor set when A at the alphabet has at least two elements. But still, A is finite. So then we introduce the dynamics on that. So little sigma denotes the shift operator, and this shift operator takes a sequence in A to the Z and shifts the entries of that sequence one position to the left. So we simply re-enumerate all positions in our B infinite sequence in such a way that if this is X, then sigma of X is equal, here is the position 0. So now a new sequence has a position 0, X1 of the previous sequence, right? So everything is shifted one position to the left. So this is now a homeomorphism of this compact metric space. So this is a homeomorphism. And we may consider various subsystems. So what are subshifts? So subshifts are, or shift spaces, that's a synonym. That's a synonym. So a subshift is a subset of A to the Z, which is non-empty, closed in this topology, and is shift invariant, which means that sigma of X, the image, is the same as X. So restricting sigma to X gives us a auto-homeomorphism of X, and we obtain the topological dynamical system. So in general, for the rest of the talk, a system or a TDS, topological dynamical system, is a pair, say, ZT, where T from Z to Z is a homeomorphism, and Z is compact metrizable. Okay, so shift spaces, so subshifts of the full shift over the alphabet A are special examples of shift spaces, of systems, of topological dynamical systems. So now, what is the natural notion of isomorphism of that systems? So the natural notion of isomorphism, so if I have YS and ZT are two systems, So when we consider them to be the same, is we consider them to be the same if they are so those two guys are isomorphic or topologically conjugated if there exists phi from y to z, which is again a homeomorphism, and this phi has to turn the following diagram into a commutative diagram. So this simply means that if we apply est first and then phi, then it is the same as if we apply uh, phi first and then t. So such two systems are isomorphic. And then let us consider the space S. So now we can imagine that we have the space S as H. It's over a given alphabet. A is the family of all subsets of A to the Z such that X is a subshift. So this is a family. One can ask, okay, if we can some structure on that family, and the answer is yes. We can observe that every subshift is a compact, non-empty compact subset of A to the Z, which is a fixed point as a subset for the induced operator, for the operator induced on the shift on all compact subsets, right? If we have a homeomorphism from a compact metric space to itself, we can now consider this induced action of that homeomorphism on compact subsets. So basically, that's a family of compact sets, non-empty compact sets, which are the fixed points of some continuous homeomorphism of the space of all compact subsets when we put, I don't know, Vitoris topology on this space, or if you know under other name, this is the same in this case as the topology given by the Hausdorff metric. So actually, this shows that SHA is actually, again, with the Vitoris topology or Hausdorff metric, it's again a compact metrizable space. So we have a structure on that space, and
So, Dominic,
yeah,
so more concretely, can we think about it in this way that two shift spaces X and Y are close to each other if the set of words of length n agree for
this is
large
exactly
n?
that topology. Yeah.
Okay.
This is okay. There are many ways to phrase it. They are in some, well, quite elementary way. Those are equivalent. So if you start writing down the definition of the Hausdorff metric, you will see that yeah, that's exactly the same. So we have those subshifts, and this is a compact metrizable space. And now the isomorphism. So, well, we look at equivalence relations now on a space. We look it in the set theoretic manner. So an equivalence relation is actually a set of all possible pairs of X and Y such that X is a subshift which is, as a topological dynamical system, isomorphic with Y. So this gives us an equivalence relation on a compact metric space. And why we are doing this is because we want to have the framework. Within that framework, we want to decide what does it mean to classify. So classification is a very general term which belongs rather to meta-mathematics than mathematics. But whenever you decide on the exact or rigorous meaning of classification, this becomes a mathematical problem, right? So usually in the traditional mathematics, often to classify means that there is, there are different meanings in different fields of mathematics, because the most strict sense of classify would be to find an algorithm working in the finite time such that if you feed as the input this algorithm with two objects of interest, then this algorithm will provide you an exact answer whether those two objects are isomorphic or not in a finite time, right? But this requires your subject to be countable, because, well, we can only represent, we only have at hand only countably many finite algorithms, and only countable number of objects can be represented in a finite way in order to be fed to an algorithm as an input, if this algorithm is going to work in a finite time. So this way of classification is a little bit too strict. But now we have this notion of isomorphism. So we can think of the following picture, that we actually have the space of all subshifts, and now our equivalence relation gives us a partition of the space of subshifts into equivalence classes. So an important observation which comes from the nature of the shift spaces in hand is that for every x which is a subshift, we know that the equivalence class of x with respect to this isomorphism relation, that set is countable. So this is smaller or equal than Aleph 0. So this is a property, this comes from a special nature of shift spaces, is that each equivalence class over a given alphabet, that's a countable set. So we now have a partition, and for us, like, what could be a nice classification theorem? That would be what? That would be a nice function. This is again. So imagine that we have now nice function from the space of all subshifts into the real line. And this nice function has the following property, that it agrees for two subshifts, even only if they are isomorphic. Then what would mean in this way? That we have a nice invariant. This number would be called the invariant of the subshift, right? And this invariant will work in the following way. Whenever we are able to compute that invariant, it tells us everything possible about the equivalence class of our subshift. Namely, whenever we are able to compute that invariant for two subshifts, then this invariant gives single at the same answer, even only if those two subshifts are isomorphic. And if we have such invariant, and this invariant is sufficiently nice, then certainly we would say that, okay, the classification problem is solved. because we could say that we have a way of deciding whether this is. And then what would mean to deciding then depends on our notion of a nice function, right? So of course the strongest notion of a nice function is a function which would be algorithmically computable, and then there are various notions of those functions, but still those notions are too strong for our purposes. And because yeah, but in some sense there is a rational consensus among mathematicians. Again, this consensus belongs to a meta-mathematics rather than mathematics, is that the next nice class of functions are Borel functions. Why Borel functions? Because Borel functions are, well, every Borel set in a compact metrizable space, or in more generally in a Polish space, arises from a countable procedure. So you start with all open sets, and you add all closed sets which are complement of all all open sets. And then in the next step, you take all possible countable unions and intersection of what you have received in the previous step. And then you moved one step forward. Then you again close this family by taking complements, but it doesn't matter really at this moment. And then you say, okay, maybe some new sets were added to my family. So now I have to take another step, take all possible countable unions and all possible countable intersections. And then you can repeat it countably many times, meaning that you run all out of finite ordinals, and then you may take the step omega, which is the first infinite ordinal. Namely, you can take all, you can consider all countable unions and all countable intersections of all sets you obtain in some finite set, and then you reach this limit step in the how this called this ordinal induction or
Transfinite induction.
transfinite. I forgot the English name. Transfinite induction, right? So there's a theorem which says that that all Borel sets on a complete metrizable, separable completely metrizable, separable topological space, all Borel sets you can obtain in this countable protocol. And if we agree that this means that you can somehow inductively get better and better approximation of your family of Borel sets. And then again, the rationale here is, okay, this so producing Borel sets requires infinite number of steps. Okay, but this number is still countable, and then there is no full axiom of choice required to produce Borel sets or Borel functions. So you can imagine that those are kind of a mathematical computers or mathematical algorithms working on countable data and requiring countable number of steps. So this is still considered to be nicer than just the general things you can obtain using, say, axiom of choice, which does, well, axiom of choice in full force says that you have to believe that something exists, and you have no way of obtaining that. So this is actually the way we would like to think so the uh, the main message from our result is that so if such a function, Borel function exists, then we say that the equivalence relation or all subshifts given by I will always write equivalence relations as pairs, the domain and then the relation. So we say that this equivalence relation is smooth. And then this is our theorem. So this is actually a color of our main theorem because we've got a much finer result than that. But let me start with this first approximation. And then maybe in the countably many steps, we will get there. So the main theorem is that so now the same stuff is that we can replace the shift space by some of its subset, provided that we have a subset which is saturated with respect to the isomorphism relation. And okay, specification, which we are again getting closer to define, specification means that if I have two shift spaces, I know that those two shift spaces are isomorphic, and one of them has specification, then the other also has specification. So the picture I draw applies as well to the shift spaces with specification. Also, equivalence relation divides this family into partitions this family into disjoint subset, and we may endow this subset with the induced topology. This turns out to be again an this can be considered to be a Polish space. So we again have the situation that we have a Polish space and an equivalence with countable equivalence relation with countable classes on this Polish space, and we may ask, okay, is that relation is smooth? And the main well, our result in this respect is negative. So we say that the shift spaces over the alphabet A with the equivalence relation given by the isomorphism, this is not smooth. So it is impossible to find any reasonable classification in the Borel way. So this is a negative result. And what else? It is like we can take even A equal the smallest possible alphabet in which the result is non-trivial. Okay, so let me now say a few words about more details. So now,
Shilpak, hand is raised. You have a question.
Yes, I have a quick question. So I itself is Borel, do we know?
yes, I itself is Borel, and yeah,
Okay.
I itself is Borel
Okay.
as a subset of the product space. Yes, this requires a little bit of this is not like exactly. It is straightforward, but it requires some care in writing down all the definitions to check that maybe not I is Borel, but the harder part is actually to see that the family of shift spaces with the specification that then they form a Borel subset of the all shifts with all shifts with all shift spaces, right?
Okay.
And then it is known that then the yeah. So that's
I
one thing.
guess sort of the vague understanding that conjugacies have to be generated by sliding block codes. They're countably many sound sliding block codes, and then you just put down some conditions, and these are countably many conditions, and you need to just make sure that it's intersections, unions, and that would be actually a
Yeah.
proof, I
So
guess.
basically, in all those cases, you can check that something is Borel by definition. But usually it requires some attention at least. This is at least for me this is not that I can see it in 3 minutes. I maybe 15 minutes and pen and paper. This is this kind of exercise. Okay, so now how about those shift spaces? So now let me go back into so now if I have again my alphabet and imagine that any finite sequence of elements of A, so an element of the set A to the power n to the Cartesian product, I will write it as simply without any parentheses or commas, like simply a sequence I1 and A1 is a word of length n, right? And then it is important notion that we say that a word W equal W1 Wn in an appears in a sequence xk, k is to the z in a to the z, if there exists a one place in my sequence, if there exists j in z, such that if I start looking at letters appearing starting from the position j in x, then I will see exactly my word. So if I had this picture here, then any subblock occurring in this B infinite sequence is a word appearing in my sequence. So now if I have a shift space, then I can define the language of the shift space. It is the collection of all words that appear in some x in x. And we also can consider the silly word, which is the empty word, and empty word appears everywhere always. This is our convention. And otherwise, we see that this family of finite blocks is an important feature of every shift space. In fact, this family determines the shift space. So now what is the definition of specification? So the shift space has the specification property if we have the following: if there exists a single length k, single length L, which is an integer greater or equal than 0, such that for every two words U and W, which do appear somewhere in some points of my shift space, there exists a single V, well, not a single, but there exists some V, which is a word of length L, with the property that UVW again belongs to LX. So it means really that whenever I see two blocks somewhere, then I will find a gluing word of exact length K with the special property that now the concatenation of three blocks UVW appears in one sequence X. I will see those words together. So anytime I see two different words, I'm sure that they will appear in one sequence at the distance K. And because we are really dealing with homeomorphic two-sided shift spaces, then clearly, if I know that those two words appear at the distance exactly K, I can easily prove that this is equivalent, that those two words will appear at the distance K or greater from each other. So specification tells you that you can take two words, put them together, just making sure that they are the distance K from each other at least. And if you put them at this distance, that you can find some filling of the space between those two words, such that with those places filled in by concrete letters, you will see again a word in the language. So this is a property which is very important in topological dynamics and in thermodynamic formalism, because first of all, it was introduced as a property which appears on every basic set of any uniformly, well, its topological version appears on every basic set of every uniformly hyperbolic system. And then all mixing shifts of finite type, for those of you who know those examples, they are not important for the rest of my talks. So let me just say that, okay, there are many examples of the shift spaces with specification, and more general, there are many examples of topological dynamical systems having the topological version of the specification property. Not all systems have that property, but it is surprisingly common, especially when you think of it that this is extremely strong. So this is a property, but okay, we don't have really much time to talk about history here. You should take my word here that this is happening. Yeah.
So Dominic, in my announcement, I gave a starting time, but I did not give an ending time. So
Yeah,
there's some flexibility. There's some flexibility.
Yeah, but okay.
You should go ahead.
1 hour. 1 hour is okay.
Yeah, so I think 1 hour is yeah, sure.
Okay. If it is not, well, too long, it's okay. So now what else? Okay, so or maybe yeah. So now we are here, and this is the specification property. So what is now a trick? So just to tell you something more, it is like if we now have two, let us consider a little bit more general situation, and let us consider two equivalence relations on Polish spaces. And now so E is a subset of Y times Y, F is a subset of Z times Z. And now we say that this one equivalence relation is Borel reducible to the other. So we read this as Borel reducible if there exists a Borel map such that for every y1, y2 in Y, f of y1 is in the relation capital F with f of y2, even only if y1 is the relation E with y2. So we see that this is just a generalization of a definition of a smooth relation. A relation is smooth. A relation YE is smooth if this relation YE is Borel reducible to the identity relation on the set of real numbers. So we see that now we have a way of comparing two equivalence relations according to our notion of computability. So you can think of it right now like this, that if I have my two spaces, here I have my one relation, here I have my second, so here I have my one relation, but I don't know it. So let us write it this way. And now what is happening? I pick 2 points and I use my function to translate my points into the other equivalence relation. And imagine that the answer whether those 2 points belong or not to the same equivalence class on this side is decidable in some way. And now the property of my function tells me that if I can decide whether those two guys are in the same class or not, then immediately this resolves my original problem here. So this Borel reducibility is a way of making precise the following statement, that the equivalence relation given by the relation E on the space Y is not harder than the equivalence relation given by Z on F. Right? If I can, so if I can solve this bigger one, then I can solve this easier one. And now it turns out that actually we have a way of deciding. We have a way of deciding. We have a way of deciding how complicated our Borel equivalence relations according to some partial order of complexity. It can be proved that smooth relations are the easiest ones. Namely, every two smooth relations are kind of equivalent to each other in the sense, because now we can also define what does it mean for two equivalence relations to be let me write it like quickly like this, that the Borel reducibility means that we have Borel reductions in each direction. So we have, and now this gives us some kind of a equivalence relation on the set of all Borel equivalence relations. And we can try to compare classes of this equivalence relation according to the complexity. So the easiest ones are smooth. So let me define the next notion. YE is a C-bar, which stands from a countable Borel equivalence relation if is a Borel subset and all equivalence classes are countable. So we have this kind of way of comparing complexity of countable Borel equivalence relations. And we, on this picture, the spaces of countable Borel equivalence relations has this lollipop structure. So we know that smooth relations, they have exactly one successor in this order for countable Borel equivalence relations. Those are hyperfinite countable Borel equivalence relations. So when a relation is hyperfinite, even only if every this is a countable union of finite equivalence relations, meaning that such equivalence relations that every equivalence class is finite. So every smooth relation is hyperfinite, but not every hyperfinite relation is smooth. So the example of a not hyperfinite relation is that we consider the set of all one-sided 0-1 sequences so with entries with 0-1, and then that's another way of defining Cantor set. And we have the equivalence relation, which is the tail equivalence relation. So we say that two sequences are in a relation E1, even only if there exists capital N, such that for every m greater or equal than this capital N, xm is equal ym. This is really hyperfinite equivalence relation because you can really, for every n, you take this as a definition of an equivalence relation with finite classes. And then you see that's union of your equivalence relations.
So Dominic, I might be misremembering, but for hyperfiniteness, don't you need ENs to be an increasing or becoming
maybe
coset?
Yes. Maybe yes. It's like this example.
Yeah, it does satisfy that for sure. Yeah.
But and I don't remember if you need that assumption or yeah. I increasing, okay, increasing. Let me add this.
Sure.
It's so there are two other classes of so there is a class of amenable, and this is an actually open question in the realm of countable Borel equivalence relation is if every amenable relation is actually hyperfinite. it is known that every hypervariant is amenable, but it is possible that actually here those two dots collapse. And here is even more treeable relation. So let me also say that in this realm of countable Borel equivalence relations, we have the situation that we have also a maximally complex countable Borel equivalence relation. So what is the member here? What is this guy here? So we can imagine that we color the elements of the free groups on two elements using two colors. So this gives us the set of all configurations over the free group with two colors. And a free group acts on that by shift. So we take a full binary. So for people phrased in symbolic dynamics, we consider the full shift over over the alphabet with two elements over the free group. And we every countable group action induces an Borel, well, every countable action of a discrete group by homeomorphisms of a compact space induces a countable Borel equivalence relation in which two guys are equivalent even only if they are in the same orbit of the action. So the most complex countable Borel equivalence relation, this is an equivalence relation such that every other countable Borel equivalence relation, Borel reduces to that relation, is the equivalence relation given by the orbit equivalence of the free group action on the configuration. So orbit equivalence on the full shift over the free group. That's the most, yes?
Sorry, I didn't understand the definition properly. So the most complicated is just the so two elements of the shift space are equivalent if they are in the same orbit. And this
Yes.
is the most complicated. Okay.
So in other words, okay, you have the space 2F2, right? So this space is actually the space of all paintings of the Cayley graph, or you paint vertices of the Cayley graph of the free group on two elements using two colors, and you act by the free group by translating those pictures. And two pictures are now equivalent, even only if they come from the one can be moved onto the other by the translation of the free group by an element of a free group. Okay, so that's the most complicated. And actually, the more refined result we have is that the equivalence relation of the shift spaces with specification is above that. So I refrain from stating the exact definition of treeable and amenable right now, because I don't think it will add anything new to what I have said so far, but we know that it is here. So now in the remaining time,
So when you say here, actually, I didn't catch what you meant by here. Here meant this orbit equivalence relation for the full shift?
The orbit equivalence relation of the shift spaces with specification is not treeable.
Is not treeable. I see.
Not treeable. So we don't know exactly where it is, but we know that it is not like this is kind of a not among the simplest ones. In particular, it is not smooth, it is not amenable, it is not treeable, it is not hyperfinite, therefore. So
I see.
it's we I would dare to conjecture, and for some time I thought I proved that, but I was wrong. There was a fatal gap in my proof, that this is actually maximally complex one. So I still believe that this is true, but I cannot push the proof to the end. It is known by the result of Clemens that the equivalence relation, the isomorphism relation on the space of all subshifts is this maximally complex. But in order to prove this stuff, Clemens uses subshifts which are extremely pure in terms of dynamics. The complexity comes from clever arrangements of periodic orbits. But dynamically, it's simply a shift space which look like that you have a fixed point, you have a plenty of homoclinic orbits, and a bunch of periodic orbits. And basically, complexity comes from the clever coding of the structure of the free group into those periods of those periodic orbits. It's a very clever construction, but it only cares about some dynamics and sacrifices simplicity of that dynamics. So you know, it is for example, they are known examples that adding some additional conditions makes the equivalence relation in dynamics more complex. For example, for the circle, if you look at homeomorphisms of the circle which are minimal, or if you in general look onto the minimal topological dynamical systems on the circle, then this topological equivalence relation is smooth. The only invariant is the rotation number. But if you look into the space of just transitive, not necessarily homeomorphic, not necessarily minimal, then it becomes for sure not smooth. Well, one can prove that it is not smooth. So it is possible that somehow more complicated dynamics are maps with more complicated dynamics are easier to classify, and the complexity then comes from the fact that for the maps which they do not have a condition like transitivity or minimality, which requires the dynamics to be a little bit more homogeneous, you can produce complexity of the equivalence relation by taking simply many independent pieces and combining them together. And the complexity comes from this partition and not from dynamics. So this is why I found it interesting. It's like, because again, we have some suspicions that say smooth maps on the interval due to their smoothness will be easier to classify up to topological conjugacy than non-smooth ones. So now I haven't talked much about proofs, but proofs are really now all proofs, they have two components. One component is to using general results of so how you prove that something is complicated here is So what would be the proof of the conjecture that this so the proof of the conjecture would be to find a mapping which comes from this colorings of the free group, right? And we need a map which is Borel and which encodes every orbit, every configuration over the free groups into a shift space with specification. And this encoding should go in the following way, that if I have two configurations here, I don't know, omega 1, omega 2, then those two configurations come from the same orbit of the action. So gamma omega 1 is equal omega 2 for some gamma in the free group, even only if the corresponding shift spaces are isomorphic. And those shift spaces should have specification. So every time you resolve such a problem, the method of proof, the blueprint for a proof is easy, one would say. But the whole hard part now lies on the part of dynamics and constructing this example, because you have to have you really need to. This is a coding problem, in fact. You really need to encode the information given here into the dynamics in such a way that this encoding preserves information about equivalence relation in the domain. Okay, so yeah, I would like to maybe stop here. As I said, I hope that I will be able to give some more details about the proofs, because some of those proofs are possible to present, but maybe we can leave it for another time.
So first, let's thank the speaker for the wonderful talk.
Thank you.
Questions? You can just unmute yourself and ask.
Wonderful talk, Dominic.
Thank you. Hi, Anima. Thank you very much.
Yeah, so I would have really actually be interested in going through the proofs. But as you said some other time, so maybe we can have your talk another time for just the proofs.
If I will be allowed to just somehow assume some basic facts, then we can have this talk. No?
So Dominic, I don't know, do you have time right now?
Well,
so we can have a further extended session after this. Like I am free and available. I don't know about others. And I would be interested in hearing more about the proofs for sure.
I want to hear about the proofs, but I have actually some meeting with some students. So this is like an extended class right now. So right now is not the correct time for it, but definitely I'll be interested in hearing the proofs.
So maybe what I'll do is I'll have a recording of this. So I'll upload this on YouTube. So
that's
if
what
Dominik allows, if Dominik is fine.
Yeah, so okay, I'm fine, because so please pause the recording for a moment.
Sure. I will pause the recording. Give me a minute.
So of course you can share it with Anima, but maybe not publish. Okay.
In that case,